Tautological.
Okay. Thank you very much. But first, I would like to thank the organizers for the invitation. It is a great pleasure for me to visit Moscow. Okay, so I will talk about topological relations. So those are mainly relations in the dimensional space for the computation model space curves. So if we take MGK bar to be the model space of genus G stable curves with key marker points, then we know that there is a topological lambda over this model space. So the fiber of this one bound over this element. So this element C is a nodal curve, and X1 and Xk are smooth marker points. They are distinct from each other. And so the fiber over this element is just the cotangent space of this domain curve C at this ith marker point. And then we can take the first curve class of this lambda. So we denote this by psi. So these are the psi classes. Of course, there are some standard maps on this model space. So there are two types of gluing maps. First, we can glue two different curves along marker points. So this, then the genus will to be the genus of the sum of the genus of previous curves. And number of marker points is the sum of number of marker points and -2. So there's also another type of gluing map. So this is just you glue two marker points on the same curve together. Then the genus will increase by 1, and the number of marker points will decrease by 2. So these are some nice gluing maps. There's also forgetful maps, so that you can forget a certain amount of marker points on this module space, and you stabilize the resulting curve. So the topological mean of this module space curves is the smallest rational subalgebra of the theorem of this module space, which contains psi classes and is also closed under the push forward of forgetting maps and gluing maps. So that's a quick way to define what is topological ring. And there are also some natural classes on this module space which are very important. Those are called the boundary class. So to define boundary class, we have to look at the dual graphs. So if we start from any stable curve C, we can define a dual graph of this curve. So the vertices in this graph is just one-to-one correspondent with the irreducible components of C. And the edges of the graph are corresponding to the double points, the nodal points of this C. And the legs of the graph correspond to the marker points on this C. So this here is an example. So this example of genus 3 stable curve with 3 marker points. So X1, X3 are marker points. So we have 3 vertices. So that's 3 irreducible components. So this gives us 3 vertices, and each vertex is represented by a small circle. So the number inside the circle will represent the genus of each irreducible component. And we have 2 nodes, which give us 2 edges connecting these 2 vertices. And we also, the 3 marker points just give us 3 legs. So that's one way to see the dual graphs. If we look at the set of all curves whose dual graph are isomorphic to a given graph G, this of course is a subspace in the dimensional space, and you can take the conclusion of that. This gives us a homomorphic class. Of course, you can take convertibility and get homomorphic class, and we call those classes boundary classes. So the relations among powers of psi classes and boundary classes for the topological relations. I should say that when I talk about topological, so this definition of topological relation of course is too restrictive. So the algebraic geometers, they also consider a larger class of topological relations, namely the allowed kappa classes and the lambda classes. But since I'm interested in Gromov theory, and the kappa class and lambda classes, they are not naturally appear in Gromov theory. So when I talk about topological relation, I mean this very restrictive sense of topological relation.
But when you say the class where is an element of what?
It's a class of the Chauvin.
Sure.
Chauvin, or if you, or for some with differentiality, just think it is cohomology class.
So there is a possibility to enhance these boundary classes with the psi classes attached to the mark points of those.
Yeah, we also consider the psi class attached to edges, half edges. Yes. So the definition is in the same way. So the major interest, I got interest in this at least, is because the application of this topological relation to Gromov events. So I just briefly reviewed the definition. So suppose we have a compact symplectic manifold V with a compatible almost complex structure. And then if we fix degree 2 homology class on two non-negative integers G and K, we can define the modular space of stable maps. So each element in this modular space consists of three parts. The first part, C, this is a genus G complex curve with at most nodal singularities. The second part is a set of K distinct smooth points on C, which are called mark points. And third part, of course, is a stable pseudo-holomorphic map from this curve C to this symplectic manifold V. And we require the homology class of this map to be equal to this A. So that's the modular space of stable maps. It has similar structures than the Magdalene space. So first, if we fix an integer I from 1 to k, we have this evaluation map. So this is a map from this modular space to the symplectic manifold V. It maps to each element to the image of the ith mark point under this pseudo-homomorphic map. Okay. So that's the evaluation map. There's also topological line bound as we had before. So this is just the fiber of this line bound over this element is just the cotangent space of the domain curve at the ith mark point. Okay. So now if we have K cohomology class gamma 1 to gamma k of the symplectic manifold, and also if we have K non-negative integers n1 and k, we can take the nth power of the Chern class of EI, first Chern class of EI. We can also pull back the this cohomology class gamma I by the evaluation map. Okay. Then we multiply all these things together. This just cut products. So multiply together, then integrating over the Walsh fundamental cycle, we get a number. So this number is called the descendant Gromov events of the symplectic manifolds. Okay. So the version fundamental class, of course, it's this actually depends on the complex dimension of the symplectic manifold. Depends the genus. The first Chern class of the symplectic manifold is evaluating on this homology class A, and also depends on number of mark points here. Okay. So there are many constructions for this virtual fundamental class. So in symplectic geometric size, there are construction by Etienne, Uno, Ruan, Siebert. The algebraic geometric side, they are constructed by Etienne and Baron Fataki. And so that's of course the Gromov events. We also studied the generating functions as we have heard in the first talk in the morning. So this is similar. So first, this is a function which so to define this function, we have to fix the basis of the space of cohomology class. So it's gamma 1 to gamma n. Usually we take the first cohomology class to be the identity of the usual cohomology ring of the manifold. Then we can define this genus G generating function to be a formal power series whose coefficients is given by this descendant Gromov events. It also depends on infinite many parameters T and alpha. And of course, it depends on this parameters we had. And here, QA is just the element of the ring. which is intended to avoid the convergence problem. It makes sense into the sum, right, or A. And so this parameter we have T and alpha. Of course, this alpha is not a power, it's just index. And we can think about this T and alpha to be coordinates on infinite dimensional vector space, which we call big phase space. So then there's a natural map from the space of stable maps to V to the Dirichlet space. It's just you take this element here, just forget about the map F. Then of course the curve may not be stable. You have to stabilize the resulting curve. Then you get an element in the Dirichlet space. So that's a very natural construction. But from this very natural construction, we have a lot of nice properties there. So this is basically the properties which is encoded in the cohomological field here. Okay. So suppose you have a tautological relation on this Dirichlet space. So that's the tautological relation in this restrictive sense I talked about. No color class, no lambda class. Okay, just the psi classes and boundary classes. Okay. Then there's a canonical way to get partial differential equations for this generating function from middle bands. And those equations, they actually hold for the Green-Witten theory of all compact symplectic methods. So therefore we call them universal equations. And in fact, they actually hold for a much larger setting. And they actually hold for all cohomological field theories, for example, FTR theory too. So, so that in that sense, it is really have a lot of implications for such relations. So, so we can take a simple example. So if we look at M04 bar, so this is just isomorphic to a P1. Okay. Now we have three boundary class, which is represented by nodal curve with only one node. Okay. And the different boundary points differ from each other just by the labeling for this marker points. Okay, so and then there's of course a simple equation. A simple fact says this different boundary points should represent the same class. So there's a very simple relation. But this simple relation, when you translate this to universal equations, will give us a very interesting equation, which is called the WDVB equation for the genus zero function. And of course, it's actually give the associativity for the quantum cohomology for the symplectic methods. Okay, so that's the form for WDVB equation, just third order nonlinear partial differential system partial differential equations. And here it involves a quantity eta. So this is just the intersection period on the manifolds. And we also use upper indices for the interest of the inverse matrix of eta. So that's why we use this map up to match up the different indices. I can say also the repeating index should be summed up. So this equation actually gives us a lot of non-trivial things. For example, if a manifold is nice enough, for example, take CPN, we can actually use this equation to recursively compute the number of rational curves in this manifolds. Okay. So for the details, I'll skip the details here. So, but it is indeed a very useful formula. So, although it's very simple. Okay. But the geometric application is simple. Geometric applications, so it's very important. Okay. Now, so I want to try to first to see how we actually translate topological relations to universal equations. So for that first, I will introduce some notations. So those notations are not very standard notations. Many used stuff in my papers. So, so first, I want a notation which generalizes the partial derivatives of these generated functions. And so if I take the vector fields on big phase space Wi, of course, they are linear combinations of these coordinate vector fields with some function as coefficients. Okay? Then this this notation W1 to WK put inside the double brackets. This just means you take the partial derivatives and multiply by the corresponding functions. The good thing about this is really defines a tensor. It defines a K tensor on the big phase space. It's actually the Kth covariant derivative along this vector fields of this generating function with respect to the period connection. To put it in a fancy way, we call this.
What are these functions?
Because if you give a vector fields, this function either by expanding these vector fields along this coordinate vector fields. So, I call this key point functions, and usually this notation, the coordinate vector fields, we also just identify this abstract symbol tau and gamma alpha. So that's the symbol we already used when we define Coulomb weighting values. Okay. When n equals 0, we just simply denote this by gamma alpha. And here we call gamma alpha to be the primary vector field, and tau and gamma alpha to be the descendant vector fields. So n represents the level of descendants. Okay. So now we can define a product on the big phase space for vector fields on the big phase space in this simple way. So if you have two vector fields, W1 and W2, I define the product of this to be equal to these 3-point functions, then times gamma alpha. Here, gamma alpha means you raise the indices of gamma by this inverse of the intersector here. These products turns out to be associated again due to this simple relation M04 bar, which corresponds to the generalized version of the WDVB equation. Right? However, well, I should also say, so when we restricted this, so we can think about the space of cohomological class of V as a finite dimensional subspace of the big phase space, okay, as the space which is morphic to all the second points where T and alpha equals 0 and bigger than 0. So therefore, this is usually referred to as small phase space. And so when you restrict this quantum product on this small phase space, it gives the product for the what is called big quantum cohomology in the literature. So the terminology is a little bit confusing. So the big quantum cohomology is really restriction of this product we define to small phase space. However, this we know that for the quantum cohomology, there's a identity. Okay, so that's the identity for the Euro cohomology, classical cohomology. But for this quantum product on the big phase space, it does not have identity. It just look at this definition. So there's no descendant there. So there are no way there exists any identity. So the best possible choice for the identity is given by these string vector fields. Is equal to the sum of this coordinate vector fields with the multiplication by this Tm alpha with m with the level of descendants increased by 1. Okay, so this T to the alpha n just means the dilaton shift. So it's equal to a shift by 1 when n equal to 1 and alpha equal to 1. So this is actually the best choice for the identity, although it's not really a choice. Okay. Now we can define a shift operator on the vector fields. So if you have this vector field which is written as a linear expansion over this coordinate vector fields, and tau plus or tau minus just increase the level of descendants for the vector field by 1 or decrease by 1. Now we can define another operator T. So it acting on any vector fields is just equal to tau plus W, and minus S times tau plus W. So if S is identity, that's our presupposition because here F is not. So there, this capital T really just measure the difference for the string vector fields from a true identity. Or you can also write this out, without using the string vector fields, using the 2-1 functions, the same thing. So the reason I introduced this operator is that it really replaces the psi class in the topological relation, or we translate the topological relation to universal equation for Coulomb weighting events. So we can look at, again, a very simple example. So if I look at M03 part, so this is this is really just a point, right? So therefore, the Chern class of any line boundary is going to be 0. So all these psi are equal to 0. But this is really simply very, very trivial tautological relation. When you translate this to Gromitian events, we get a highly non-trivial equation, which is called the genus 0 tautological recursion relation. In the first talk by Professor Kazarian, we heard about this terminology tautological recursion, but this is actually different from what we have here. Actually, this terminology comes first. Okay. And that Oriental tautological recursion really comes later. So this is the terminology used by Wheaton, for example, at the beginning for the Gromitian theorem. So it just says if you have any 3 vector fields, when you apply T to any one of them, and put this into this 3-point function, genus 0 function, it always equals 0. And we can also observe that this genus 0 topological recursion relation is actually implies the generalized WDAV equation. So therefore, in the genus 0 case, we only have one essentially only one universal equation. That's the topological recursion relation. This very simple topological relation, they also give us very interesting applications. So this is application which is related to conjecture, which we call the Virasoro conjecture. So the Virasoro conjecture says that if you have any smooth projective varieties, then we can construct the infinite sequence of differential operators Ln, where n is bigger than or equal to -1. So these are differential operators acting on the space of function on the big phase space. And so with a slight modification given by Shell and Katz, these operators actually satisfy this Virasoro bracket relation. So the bracket of Lm and Ln is equal to m minus n times Lm plus n. Here, Lm will depends on the first Chern class of the symplectic manifold. It also depends on this intersection here. And then if we sum up all the generating functions of different general with the insertion of an extra parameter lambda to 2g minus 2 power, then takes exponential. We can call this function z. So this is the partition functions in the by physicists. Okay. And then this Virasoro conjecture just says that if B is any smooth projective variety, then all this infinite sequence of differential operators should kill this function z. Okay. So this equation is called Ln constraint. Now,
you defined Gromitian invariance for symplectic manifold.
yes.
Is it correct that there is some conjecture is expected for smooth projective variety, but not for symplectic?
I will mention this later. In general, not for symplectic manifold is not correct. Okay. The reason is that this Virasoro bracket relation is no longer true in general symplectic manifolds. So there's an actual constant, adding to that bracket relation. And so that says the general you cannot hold this character general symplectic.
So that means there are examples where it doesn't hold?
Yes.
No.
Yeah. Okay, so L minus 1 z equal to 0. So that's the first equation is actually a known equation. It's also called string equation. This just tells us how to compute the Gromitian events when one of this insertion is the identity. So it's very simple. This is not true for symplectic manifolds. Okay. And the next equation, L0 equal to z equal to 0, is also true for all symplectic manifolds. It's a combination of two basic properties for Gromitian events called the dilaton equation and the divisor equation. And they are these two actually are holds for all complex symplectic manifolds. So in a special case, if this manifold is just a point, then this Virasoro conjecture turns out to be equivalent to Wheaton's conjecture, which says that this function z should be a top function of PDB hierarchy. Although Wheaton's conjecture was first proved by Kontsevich, and then later now has many different version of proofs. So you can see that Virasoro conjecture is really a very vast generalization of Wheaton's conjecture in that sense. And we can also expand the universal constraint. So this LNZ equals 0 respect to the power of lambda, and you can make sense of universal conjecture for each genus. Okay? And then in 1998, Gang Tian and I actually proved this result, which says that the genus 0 universal conjecture actually holds for comparison mathematics. So the reason the contradiction I just mentioned, the bracket has an actual constant, turns out does not affect the genus 0 part, but it will affect the genus 1 part. So in genus 0 part, we still can hold this is correct for both eigenvectors, but not for higher general. Right? And in our proof, of course, besides this basic properties, string equation, Philipson equation, divisor equation, all what we use is just this genus 0 topological recursion relation. So that tells us this genus 0 topological recursion relation, all this very, very simple, that has very nice applications. Okay, then what happened for genus 1? So in genus 1, there's of course also topological recursion relation. So it's corresponding to this simple equation for topological relation of this M1 bar. Okay, so M1 bar, there's a one psi class. It is equal to 1 over 12 of this unique boundary class. Okay, if you translate this to a universal equation, it just means T applies to any W when you insert to the genus 1 function is equal to 1 over 24 of these 3 points genus 0 function. Okay. And unlike the genus 0 case, we only know genus 0 topological recursion related determine everything. Okay, but in genus 1 case, this is not true. In genus 1 case, there's another relation discovered by Gessler. So this is a relation M14 bar. So there's no psi class in this relation. It's purely a boundary relation. So very similar to the relation which we get the WDV equation. So therefore, in that sense, you can say this is sort of genus 1 analog of the WDV equation. It gives us a complicated universal equations, which involve 7 terms and 4 terms of genus 1, 3 terms are genus 0. And so I'm not going to write this out because it looks too complicated. Yeah, so when we say a manifold has some quantum cohomology, this simply means the quantum product has no important elements. Okay. So in this case, Dubrovin and Eugene Zhang, they actually proved that if a smooth projective varieties have some simple quantum cohomology, then the genus 1 universal conjecture holds. Okay. Because the key idea in the proof is that in a semi-simple case, there exists very special coordinates, canonical coordinates. So in the canonical coordinates, the Gessler equation becomes very simple. So you can essentially solve Gessler's equation. You can essentially solve F1 from F0 using Gessler equation after a constant. Then of course they just to prove the universal constraint, just plug into the universal constraint to check it whether you put a 0. Okay. So that's actually the idea how it proves in genus 1. Okay. But I should say that semi-simple case is not the generic case. For most manifolds, the quote-unquote are not semi-simple. So for instance, if you look at the curves, only sphere has semi-simple quantum cohomology. All the other curves are not semi-simple. Okay. So therefore, non-semi-simple cases are generic, not semi-simple cases. Well, to study this to take more advantage of this Gessler's equation, we actually look at this construction of Euler vector fields. So suppose, so here I assume V to be a smooth projective variety. And I take this basic vector gamma alpha to belong to the local homology class with homomorphic degree to P alpha and the homomorphic degree to the Q alpha. Okay. Now we can define a Euler vector field on this small vector field, on this small phase space. So it's essentially equal to the first Chern class of the manifolds plus gamma alpha times this T0 alpha, then times the constant depending on the homomorphic degree of the gamma alpha. Okay. Then these are of course are vector fields on a small phase space. We can take products of these vector fields. So with this I call the quantum powers with vector fields. So I use EK to denote the quantum product of K copies of E. Then it turns that these vector fields, they are also satisfy this sort of reactive relation. So this was independently proved in a paper by Hurton in the money and myself. But actually, those vector fields are not directly related to the Virasoro operator. Although there are some relations between them, which we will see later. So this is the result of myself from the 2001. So it said that if you look at the genus one Virasoro conjecture, so the original Virasoro conjecture is on the big phase space. Okay. Then this theorem just tells us you can just look at the small phase space. So namely the all invariants involved just primary invariants. There's no descendants. Okay. It does have a very simple formula. Okay. It says that if you restrict the genus one function to the small phase space, then acting on this function by the His quantum power of this Euler effect fields, it should be equal to some function which only depends on genus zero data. So which I use phi to represent that function. So that function is actually related to the sort of twisted quantum product of K minus one coordinate of E. So I'll give the details here. But this phi can be explicitly given this.
I think I looked in this paper. If I remember correctly, you assume that the manifold doesn't have optical homology.
Yeah, but that's not essential.
It's
not essential. It's just because you just try. I don't want you always define this minus sign when you switch the sign. Otherwise, there's no difficulty. But if you are very familiar to work with the super manifold, of course, you just do it the same way. Okay. Then this equation. This equation, EK identified with phi k, it actually corresponds to LK minus one constraint in the genus one Virasoro conjecture. And as before, we know that this equation is always correct when k equals zero. That's just comes from string equation. And k equals one, which comes from divisor equation. Question?
Sorry, I got lost a little bit in the previous slide. That means I take K's power and then apply as a differential operator.
No, K is a vector field. Okay, E to K power. This is vector fields. Right?
But doesn't mean I apply a vector field K times or I
No. It's you take the vector fields K times and multiply them together.
Yeah.
Using quantum products. So the result of this multiplication is still a vector field. Then you're using this vector fields acting on this function.
Yes.
Okay.
But yeah, otherwise no genus zero data.
Yeah. Okay. Okay, so the proof of this theorem, of course, only use the genus one topological recursion. So we need this formula for psi one on this M1 bar. And then we can also, take advantage of Gessler equation to prove the following thing. So if we just look at that equation for k equal to 2 case, k equal to 0, k equal to 1 already we know it's correct. We can prove the next one, k equal to 2 case, then you prove the Virasoro conjecture. So, namely the genus one Virasoro conjecture can be reduced to this very simple equation. So the quantum square of the Euler vector is acting on F1 equal to a genus zero function. So another way to see that is that this is same thing to see that if you look at this genus one Virasoro conjecture, it actually follows from the genus one L1 constraint. Yeah, again, so the key point in the proof of this theorem is that if you recall in the simple case, how to Brownie and John proved that genus one Virasoro conjecture, they proved that by solving the F1 from the Gessler equation. But in non-simple case, you cannot do that. Actually, it's not in general, it's not correct. In general, you cannot hope you can solve F1 in terms of zero. That's not possible. Okay. But although we cannot solve F1, but we can solve e to kth power acting on F1 for all k bigger than or equal to 3, in terms of E2, acting F1, and genus 0 beta. Something which is a very, very strange phenomenon, which I don't fully understand myself. Although I can prove it, but I don't know why. Okay. So that's actually how this relation proof, this result is proved. Of course, if we combine with these algebraic structures among these vector fields, and also the fact that that small free space is really a finite dimensional vector space, we can actually prove the following results, which says if the quantum cohomology of this magnitude B is not too degenerate, which I don't want to be too precise on this because it's a little bit technical. And also satisfy a compatibility condition, then the genus 1 Russell conjecture should be correct. So I will say that all manifolds with some simple quantum cohomology satisfy these conditions. And all smooth curves, they also satisfy this condition. All K3 surfaces also satisfy these conditions. Of course, we know most curves are not symmetry. K3 surface is also not symmetry. So in this sense, this theorem is actually somehow stronger than the Brownian and Jan's results. And at the moment, we actually don't know any example which do not satisfy these conditions. So therefore, I suspect that if you can prove that all the manifolds satisfy these conditions, then you prove the genus 1 Russell conjecture. But these conditions are just genus 0 condition. They have nothing to do with genus 1. It's just a condition for the quantum cohomology of the manifolds.
If you look the general framework of chronological theories in genus view, can you find examples?
I didn't find any examples. Yeah, again, I didn't find examples. Yeah, because my interest was mainly on theory. So, but I didn't look at other examples. Yeah, but at least in growing theory, we didn't find any other. We didn't find any example which do not satisfy these conditions. So that's about the genus 1 story. The genus 2 case. There's also a genus 2 topological recursion relation, which roughly says that.
You check all the surface.
No, I haven't checked all the surfaces. Because I don't move on to other things. I move on to other genus things. I did, but anyway, we have some students they really want to take this as a thesis problem. So I think it's a good thesis problem. Find the example of growing within events which does not satisfy these conditions. It will be very interesting. Okay, so in the genus 2 case, there's a similar genus 2 topological recursion relation. This was originally due to Manfred, but translated to universal equation by Gessler. It basically says that T squared, you apply this operator T to any vector W twice, and insert to this genus 2 function, it should equal the lower genus data. Okay. And so I should say this formula is actually weaker than the genus 0 and the genus 1 topological recursion relation. Because in genus 0 and genus 1 case, we can use this topological recursion relation to get rid of all the descendants. But in genus 2 case, starting from genus 2 case, that's not possible. You cannot get rid of descendants. They're always, you have to work with descendants. Okay, so that equation actually corresponded to this topological relation on the M21 bar. It's just equal to, so the psi 1 squared is equal to the linear combination of 5 boundary stratas. Again, so there's also an analog of Gessler's equation, genus 2. It's given by Palarsky and Penner. It's very complicated. So this time it has 20 terms, with 4 of them are genus 2 terms, and 16 of them are genus 0, genus 1 parts. So I'm not going to write this out. So to working with this equation, of course, is much harder than genus 0 and genus 1 case. So this equation actually corresponds to the topological relation of M23 bar. So I should say that all the genus 2 universal equations they have to involve descendants. So we cannot just restrict to the small phase space to work with primary mass. So that's actually the main reason I want to introduce this quantum product on the big phase space, just to make this framework to work better. Okay, now I prove that in 2007, I proved this result that if the quantum cohomology of this simple, the F2 actually can be explicitly solved in terms of this Manfred and BP equations. So these two the universal equations. And of course, then if you can solve that function, the progressor just plug in this to the Brosser constraint to check it. So in that way, also prove the genus 2 Brosser conjecture holds for the such simple case. But of course, the simple case for the Brosser higher genus Brosser conjecture has been proved later by Talmud in 2012, but by very different methods. And other methods we cannot hope to generalize to the non-simple case. As I said before, so most manifolds do not have simple quantum cohomology. So for example, all the curves, only sphere has simple quantum cohomology. And Brosser conjectural curves was also proved before by Ogunkov and Pending. And in general, this conjecture is still an open conjecture, it's widely open. Even for genus 1 case, it's not complete. And again, so we can also look at the non-simple case. As a proof of result, we said that for all smooth projective varieties, the genus 2 Brosser conjecture actually follows from the genus 2 L1 constraint. We just need to go, other than L minus 1, L0, there's two known ones, just need to go one step further, then solve the genus 2 Brosser conjecture. I should remind you that this the first three operators, L minus 1, L0, L1, they actually span a three-dimensional sub-observer, which is isomorphic to SL2. Okay? Of course, the first two constraints we know, right? So therefore, we can interpret this result together with the genus 1 result I mentioned before as the following. So it basically says that if you know the SL2 constraint is correct, then the Brosser constraint is correct. This was proved in genus 1 and genus 2. So this is the universal result which does not have any restriction on manifolds. And I somehow found this equation these results are a little bit surprising to me because it just says if you really look at the universal equations, it has nothing to do with the geometry of manifolds. It's a geometry of Deligne-Manfred space. Okay. So this results tells us somehow the Deligne-Manfred space, the geometry of Deligne-Manfred space upgrades a three-dimensional constraint to an infinite-dimensional constraint. So that's how I interpret these results. So based on these results, it's actually very reasonable to post some conjectures. So first, I believe that for all smooth projective varieties, the Brosser conjecture always follows our universal equations at L1 constraint, like Sukai just says. So if you look at the Brosser constraint, only L1, perhaps, L1 has something to do with the geometry of the manifolds. All the other constraints in that even-dimensional system equations actually comes from the Deligne-Manfred space, not from syntactic manifold. So that's one conjecture I would like to propose. Another conjecture I want to propose is if the manifold is semi-simple, so in that case, it doesn't have to be trajectory, it's also very manifold as I said. You can actually solve the Green-Witten inverse explicitly in using this universal equations. Again, this is also true in genus 1 and genus 2 case. But to study these problems, we actually need more topological relations. And unfortunately, topological relation becomes very, very complicated in higher genus. Takashi Kimura and I actually wrote two papers deal with these topological relations on M31 bar and M32 bar. We get this two relation with epsilon 1 to the third power on M31 bar, it can be represented as a linear combination of 29 boundary class. M32 bar, if you take psi 1 square psi 2, it's going to be equal to linear combination of 100 boundary class. So these are the results actually before Pixon's result. Pixon actually has discovered a huge class of topological relation. But there are a lot of common classes involved in that relation. So you cannot really directly apply to Gromit theory. Just have a lot of common classes. Then a former student of mine, Xin he actually used Pixon relation to get rid of common class, get this result from M33 bar for the product of psi 1, psi 2, psi 3. This is going to be a linear combination of 148 boundary strata. We also went on to M41 bar. You see this psi 1 to the 4th power is equal to the linear combination of 186 boundary strata.
How did you get the two relation?
Before we actually, so basically we use the information of, because the Gromit theory for points for CP1 is well known. We just use this information to fix the coefficients in that topological relation. But in a very next way. So you have to explicitly calculate this inverse and insert in this relations, and you get a system, of 29 linear equations that solve it.
So one gets the relation from the study of the Swiss.
Basically, you could, but Pixon has a conjecture. He said that his relation gives all the possible topological relations. But actually, this is not true. So it's not whether it's worth it to go to different higher speed curves. Yeah. But of course, there's some problem, because this is a huge class of universal equations. We have to figure out which one is new, because you can start from equation, you can get a lot of other equations. For example, you find one universal equation, you just take a derivative, you get another universal equation. It may look like very different after you maneuver. So it's
new result, like often by student.
Yeah, so that's
catch the pieces.
yeah, he just said that the known one can be derived from Pixel equation. Yeah. So that means fixed one for the known, including my result with Kimura, can be derived from Pixel's relation.
That's what's this word.
That's good. This thesis. Yeah. I also said that also in putting that words, it says in this lower genus case Pixel results doesn't give us new relation. Okay. And if you look at this lower genus case of this topological relation, it's somehow very frustrating because it's getting so complicated, it's so very quickly out of control. And but then in the joint work with Rahul and Candy, we actually found a very surprisingly simple topological relation. So this is relation. If we look at the MT1 bar, there's a psi class. You raise this to a power which is somehow bigger than equal to 2G. Then suddenly you get a very simple relation. It's just it's just a very simple boundary class. So this just corresponds to a boundary strata with only one node for the curve. And here this arrow, here this integer over the arrow means you also look at the psi, the 8th power of the psi class associated with this half edge. Okay, same thing for this here. So therefore, this is really very simple relation. And also there's some vanishing results. So this is totally supported relation, totally supported on the boundary. Again, with a very simple efficiency. And the reason actually we actually prove that was actually, so before that our work, Xiaobo Liu and Hao Qu, when we started this Faber's conjecture, we found out a lot of equations for the concept-written top function. Then we said this should be true for for the general case. And so they propose a conjecture. The conjecture system of universal equations for rating events. And that's a paper appeared in Journal of Linear Geometry, and we put this conjecture. This work, Rahul and myself intended to give a proof of the conjecture. So that's one application of this relation. Of course, also from something more. So if you look at MG2 bar, we take again psi 1 plus alternating sign times 2 to this power also just bigger than the 2G. Then they also converge for the equation. So somehow 2G is a very negative number here, which we don't know why. So above 2G, then everything becomes very simple. But below 2G is so complicated, we suddenly totally have no idea how to handle it. Of course, there are also some other vanishing results. So for a long time, besides proving Keeton Liu and Hawkins' conjecture, we actually didn't notice any application of this relation. But in recent years, these relations are related to integral systems. So in this paper by Robin, Liu, and Yang, using generally we said this relation actually are somehow related to the Hodge hierarchy. And in this Iglesia, Sheldon, also Bria and Sheldon's paper, they said this relation can be used to prove properties for the Roman-John hierarchy and also this double replication hierarchy. And also in Bria and Sheldon's paper, they also proposed 3 conjectures about topological relations. 2 of them actually involves the double replication cycle. Another one is in a more is a topological relation in this more restrictive sense. We only have psi classes and boundary classes. So I'm going to give a quick description of that. So if you look at T to be a genus G stable rooted tree whose legs are divided into 3 types. So we have n frozen legs, those are always attached to the root of this rooted tree. There are also n regular legs, so each regular leg has some negative weight. And there are also some extra legs. So it attaches to any roots which is not any vertex which is not the root. And those extra legs will be forgotten later. Okay. So we require that T to be stable after forgetting these extra legs. And this weight on this regular leg actually induce a set operation. So this is a map from the set of all half edges of this tree to a set of non-negative integers. So if H is a regular leg, then this QH is just a weight of H. And if H is not a regular leg, then QH plus 1 is just given by the number of extra legs of the descended vertex. Then the Briac and Sheldon they define this topological class. It says that you take the psi class associated with this half edge, then raise to this QH power, then push forward by this natural gluing math. Then also push forward by this forgot math, forget all these extra legs. Then multiply by -1 to the number of edges of T, then sum over all such possible tree T. Then we propose this conjecture says that if n is bigger than 2, or if the sum of all these weights is bigger than the 2G plus n minus 1, then this class should be 0. And this conjecture actually implies this function which uses to define the Roman-John hierarchy associated to an F-cohomology and unrelated differential polynomials. And we actually also prove that this conjecture holds if either the genus equal to 0, or if n is the number of regular legs is equal to 1. Actually, for the proof of n equal to 1 case, this really use this relation I have found with the Rahul to prove that relation. They also prove that this conjecture can be reduced to the case where the sum of D is actually exactly equal to 2G plus M minus 1. And all the components of D should be positive. And recently, a student of mine, Chongyu Wang, actually proved the following result is we can actually reduce the proof of this conjecture to the case where M equal to. So this actually reduces the proof of this conjecture for each genus to justify checking finite number of cases, okay, which the number of cases we need to check is equal to the number of partitions of 2D plus 1. And then in the genus 1 case, we can actually think this is correct. Okay, so I stop here. Thank you very much.
Are there any questions?
Yes.
So the first half of the talk you use equations for the potentials associated with the symplectic manifolds. Is it possible to replace this just by a metric common theory?
Yes, you could do that. But of course, you cannot do the purposes. Okay. For common field theory, so the way I want to consider the connection. But instead of common field theory, there's no connection. But I'm going to complain about this. No problem. Now this you also pick up for some 6 times 4 get one common field.
Every chat is an explicit formula for tautological relation obtained against external comparisons.
No, we of course. So what's actually the question just mentioned that is another way to analyze. So people have to try to see whether we can use fixed relation to get all the non-universal equations. That part is having done by a former student. Yeah. But anyway, it's more complicated. If you try to show fixed conjecture in your own possible relation. That's so I don't know how to. I don't think anyone has any idea of truths. Because you don't know what are the universal relations there.
Is there any reasonable software effectively tautological relations? Computer software.
Computer. Yes, so for example, I mentioned this result by Xiaobo, but you can piece of well. You fix the relation, you really write them out, it's really quite complicated. So you have to find the vocabulary of this kind of class. It's kind of highly actually complicated. We really want to do that.
There is also this agent cycle software where you can do an intersection like any classes, and it's all the relation of pixels which are inside. So you can reduce any things using the relation. I mean, increase within a genus and another part. Yeah, but until genus 1, 2 is okay. So how did you prove that? So the last one. So you mentioned that the vanishing for m bigger than 2 is equivalent to just checking the vanishing point.
Yes.
How did you get it?
We actually prove a push forward formula. It's if you forget about if you forget about one of these roots, if you forget one of these frozen x, we prove a formula how this how the push forward by this forgetting math to this polar class constructed by very and sharp, they can be represented by other class citizens. If you allow this, if you use this push forward formula, then
When you spoke about the genus 2 results, you said that you used the Malthus relation.
Yes.
Those are fun.
yes.
But yeah, I remember that there is other relation,
Yeah.
I'm outside too, by Gensler.
Yeah, there's also a Genus relation by Kessler. One of my results before shows that Kessler relation can be derived from Markov relation and balancing. So therefore Kessler relation is very extra. So that's what I mean. So how you know you really get a relation which is new from the known one. So this relation, when you first look at them, they look very different. But if you really maneuver them, you find out that the sum of them can derive from one. Therefore, it's not a great decision.
Okay, if there are no more questions, we have let us let the speaker again.